Welcome back. In this video we will talk about the k-nearest neighbors classifier, or kNN for classification. We have previously seen the k-nearest neighbors for regression. Similarly, the k-nearest neighbors classifier is not characterized by a fixed set of parameters theta. So it's a non-parametric model. And as we saw previously, there is no training as such in kNN. So we just save or memorize the training dataset as it is. Now, when you get a new data point x and you want to predict the class of x, then what you do is you just compute the distance from x to all the data points in the training dataset and then take the k training examples which are the most similar to x, or the less distant to x, the closest or the nearest to x. And to find those, we usually use the Euclidean distance. We compute the Euclidean distance between x and each data point in the training dataset. And then based on these k-training examples, the predicted label for x is just the majority label among those k-nearest neighbors. So for example, here we have a training dataset with two classes, the red class and the blue class. And let's say that we use the three nearest neighbors, so k is equal to 3. Now, given a new data point x, for example, this one, these are the three nearest neighbors, right? These are the data points in the training data set, which are the closest to x. And the majority label among those is red. So the predicted class for x is the red class. And of course, this is just an example with two classes, but kNN is a multi-class classifier, so it can be used with more than two classes. So for example, here we have three classes. And let's say that we use k equals to 7. So we use the 7 nearest neighbors. So given your input data x, this one, you find the 7 nearest neighbors, and then the majority class is in this case the blue one. So the predicted class for this new data point is the blue class. So the k-nearest neighbors is natively a multi-class classifier because it can be used with more than two classes. We can also have a weighted version of kNN. So for example, suppose that we have this data set. This is our training data set. And we get a new test data point x, like this one here. And suppose that we want to use kNN with k equals to 5, so the 5 nearest neighbors. So let's say that these are the 5 nearest neighbors of x, the data points from the training data set which are the closest to x. And so here the probability that x belongs to the red class, which is this class. So the probability that x belongs to this red class is the number of data points or the number of k-nearest neighbors which are labeled with this red class among k, right? So in this case, we have 3. So it's just 3 over 5. And similarly, the probability that x belongs to the blue class is equal to 2 over k, in this case 2 over 5, because we have 2 data points among the k-nearest neighbors which are labeled with the blue class. And this is the same as if we are given uniform weights to each of those nearest neighbors. So here we have 5 nearest neighbors, 1, 2, 3, 4, 5. And then 3 of them belongs to the red class, so 1, 2, 3. But they contribute equally to this prediction, right? So they all have a uniform weight of 1. Instead of this, we can actually define non-uniform weights based on the distance from x to each of its k nearest neighbors. So let's say, for example, that this distance here is called d1. This is the nearest neighbor to x. And let's say that this is d2. This is the second nearest neighbor. And this is d3, d4, and D5. So now instead of using uniform weights like 1, what we will do instead is to use a weight which is based on the similarity between x and its nearest neighbor, right? And each of its nearest neighbors. So for example, this point is very close to x, so we want a high weight associated to this. So we define the weight as 1 over the distance, the inverse of the distance. So this is a similarity. So we can use 1 over d1. So that's the similarity between x and this first nearest neighbor, plus 1 over d3 plus 1 over d4. Because d1 is this, d3 is this, and d4 is this. So these are the nearest neighbors that belongs to the red class, divided by the sum of all the similarities. So 1 over d1 plus 1 over d2, 1 over d3, okay, so we normalize this sum of similarities by the total sum of all similarities, so that this gives us a probability between 0 and 1. So that's the weighted version. And the weighted version for this one is this one. So here we have D2 and D5 because these are D2 and D5, and these are the nearest neighbors to X, which belongs to the blue class. And same thing, we normalize by the total sum of all similarities. You will get more details about this in the lab. Now, once you compute the probability that X belongs to each of the classes, then the predicted class will be the one that leads to the highest probability. So for example, if this one is larger than this one, then X belongs to the red class. Now here we have an example of a training dataset with two classes, the red class and the green class, and it's the same dataset here and here. But here, in this case, we train a linear classification model, for example, a logistic regression model. So this gives us a very simple decision boundary. It's just a linear decision boundary. And here we use a k-nearest neighbors classifier with k equal 1. So this is just the one nearest neighbor. And here we use the kNN with k equals 15. So the 15 nearest neighbors. And this green and red regions are defined by predicting the class of each point in this region using the one nearest neighbor. So you take this point, you use one nearest neighbor to predict the output. It's green. Then take this point, same thing, green, this point, and so on. This one will be red. So based on this, we will have a region where any data point in this region will be classified as green, and another region where any data point in that other region is classified as red. Same thing here. So that's basically a decision boundary using the one nearest neighbor. And that's the decision boundary that we get using the 15 nearest neighbors. And you can clearly see that when k is small, this will lead to a more complex decision boundary, as you can see here. So in this case, all the training data points are correctly classified, even those outliers here or this noise. But this is not necessarily good because if you get a new data set from the same distribution, new test data, then this model will maybe perform poorly. So it just performs well on the training data set, on the data on which it has been trained. But here, when k is larger, you can see that this leads to a simpler model or simpler decision boundary. And if you increase k further, for example, you go to the extreme case where k is equal to n. So n is the size of your training data set, the number of training data points. In this case, you will get a very, very simple model where the predicted class will be just the majority class in the whole data set. So for example, if the red one is the majority class, it is larger than the green one, then regardless of the input, the predicted output will be always the red class. So that's a very simple model, but it's not particularly useful. So in this case, we talk about underfitting. And in this first case, we talk about overfitting. We will talk more about this in a future lecture when we see generalization and the problem of overfitting and underfitting. But here what I want you to notice is just that smaller k produces a more complex decision boundary, and larger k produces a simpler decision boundary. And when the decision boundary is too complex, then it might achieve a small error on the training data, but it will not be good in general, because if you test it on new test data, it will produce a high error, or it will achieve a high error. And the same thing, when the model is too simple, then we talk about underfitting. And in this case, the model will not be good on the training data and also on new test data. But when k is reasonably small, right, somewhere in the middle, then you can achieve a good error. We will see later how to choose the best value for k, or the best value of any hyperparameter for any algorithm in some next lecture when we talk about generalization. To explain a bit more what we just said, let's take this example, and here k is equal to 1. So this is the training data, and this is new test data. If you use the k-nearest neighbors with k equal 1, then you get this decision boundary on this training data. And all the training data points are correctly classified, so you get 0 error on the training data set. But if you collect more data from the same distribution, you get new test data, then you see that the error is much higher, right? For example, 0.15 here. Now let's see what happens if, for example, we increase k to, let's say, 3. So now k is equal to 3, and you can see that the decision boundary is a little bit simpler, and the training error increased a little bit. But that's not necessarily bad, because the error on the test data decreased. And if we increase k further, for example, k is equal to 7, then we can see that the training error increased more, and we got a simpler model, but the test error decreased. So the error computed on the test dataset, the new dataset, decreased. So k is equal to 7 is better than k equals to 3, even though the training error increased. We will see later how to choose the best value for k by picking the one that minimizes something called the generalization error. And we will see how to estimate this generalization error based on something called cross-validation.